Hello, let's solve this LeetCode problem called successful pairs of spells and potions. So we are given two positive integer arrays, and these are all positive numbers, and one is spells and the other is called potions, and they have length of n and m respectively, and ith element in the spells array represents the strength of the ith spell. So these are the spell, which is like magic, and potions, jade potion represent the strength of the jade potion. So you can understand. So we basically have two spells and potions arrays, and uh, you are also given an integer success. And this is the success example. A spell and potion pair is considered successful if the product of their strength is at least success. So basically, we have to return an integer array pairs of length n, where pairs I is a number of potions that will form a successful pair with ith spell. So it means you have a bunch of potions here, and you have a few spells, and for this spell 5, it is the strength of the spell, and you have to find 5. You can multiply the product of 5 and 1 is 5, and this is less than 7. So this is not going to work to break the spell. Then you take 5 and see the product. 5 and 2, it is 7. It's now 10. So 10 is now higher than this number 7. So this is going to break the spell. So this is a successful uh, pair. And now you keep going. So 5 times 3 is now 15. 15 is definitely higher than 7. Then you have the 5 times 4, which is 20, which is still higher than 7. And 5 times 5, this 5 and this 5 are 25. So this is again greater than 7. So you have to return an array pairs. Basically, pairs array is going to have the same length as spell because it has to have a length of n, and n is the length of spells. So you have to return this pairs array. So for spells, it has length of 3. So you have to have a length of 3, 0, 1, and 2 at the indexes. This is the pairs array that you have to return. And for the first value, you have to count out of these 5 potions, how many can form a successful uh, pair with the spell, which is 5. So you basically have to find how many numbers in the potions array have a product with 5, which is higher than the success value. And in this example, you have seen that the first spell 5 has these products with the potions 5, 10, 15, 20, 25, and out of this only 5 is less than 7, and that means 10, 15, 20, 25. There are 4 products which are successful, so you have to return 4. For the next one, 1, you can take a pair with 1, if the product is 1, 1 and 2, if the product is 2. So basically, you're going to get a product area 1, 2, 3, 4, 5, and none of them are higher than or equal to 7. So in that case, there is no successful product, so you return 0 for that one. And the third number is 3. So for 3, the first product is going to be 3, then the second is going to be 6, and the third product is going to be 9, 12, and 3 times 5 is 15. Then out of this, you can see the first two are not going to be higher than 7, but 9, 12, and 15 are going to be higher than or equal to 7. So you return 4, 0, 3. So because out of 5, there are only 3 pairs. So this is the result. So if we want to return that, so if you can go read the explanation, what it explains. So let's look at how we can solve this problem efficiently. So if you notice spells, this pair spells, so this is going to be length n, uh, and the potions array is going to have a length of m. So in this case, you can see for each number of n, you have to search for every value in potions and then count. So if it are a very brute force solution, you can, for each one of the items in n, you can basically, for each, you can basically uh, go through the products, every value for each in the potions. So for the nectar value, and then count. So in that case, you'd end up uh, n times m products, and then for each of the m, you again have to keep counting. Uh, if there is in a random order, which one is going to be the right value. So instead of that, you could actually do a little bit better, but notice what is the time complexity for this one. For each spell L, you have to go through every value M, so you have an n times m complexity, and then for each m, you have to now count. So this is going to be order of n times m, uh, if I am not mistaken. So and as soon as you have a value, you just count and put that in the result. But if you wanted to use a better solution in the and there's a better way than order of nm time complexity. For that one, this is going to take a little more work. So first of all, imagine you have this potions uh, the potions array sorted and potions has a length of m. So to sort using a standard sorting algorithm, this is going to require a sorting complexity for sorting the potions. And after that, once you have this sorted, you can basically for each value in spells. So on this left side, you have the spells array. So for each of these spells, so there'll be n numbers of values and spells. You basically have to do a logarithmic search. So basically a binary search in the potions array. So this is going to be the new potions array after sorting, and you basically have to uh, sort using a log of m time complexity. So this is the second step. So in that case, the time complexity would be basically log of m log m to to sort the potions array, and next, then for each value in spells, which is length of n, you're going to run a binary search into the potions array. And this is still a little bit better than the order of mn time complexity you see. So this is going to be a little more efficient than order of mn, which is going to be basically like a quadratic if they have the same length. So if m and an n had the same length, and this is going to actually mean n squared value. But in this case, the left would be n log n and n log n. So if they have the same length, in the case, uh, this would be order of n log n, which is better than order of n squared. Uh, and in case this m is much larger than n, in that case the efficiency gain is even better because this is now a logarithmic term and this n is big, but your m is bigger and you are taking a log of that, so you're getting a huge efficiency gain. Uh, so that's actually good in any case. And for this one, the space complexity is going to be constant because we're not considering any extra space that we need to return the pairs array. But for the algorithm, you don't need any network space. So space complexity is basically going to be constant. Uh, you don't need to uh, go through and store the arrays or do anything like that. Now let us code up the solution. So first of all, let's define the two variables span.length and and first of all, we need to sort the portions array, and this is going to be order of m log m, and then for integer I equals 0. So this is basically going to be each of the values in n, and I plus plus our spell values. And for each spell now we have to search between the portions array. And to run a binary search, you can have a small function here, or you can just write out the whole uh, routine explicitly. So integer L equals 0, and now we have to define that length. So in case it totally does not find the end of the, it doesn't find any value, in that case, we could actually end up in the very end of, uh, so typically the portions array has values from length 0 to uh, m minus 1, but in case there is no value, we'll just end up in m. And for our basic binary search, we're going to keep searching while they are not the same. And when they're the same value, we'll end up stopping. So we have to define the midpoint. The midpoint, I like to define it using this method, r minus l, and this basically take the left value, which is an integer, and takes the difference, r minus l, which is still an integer, and take half of that value, and then add these two up. This basically avoids integer overflow, and this is a safer method in general. At this point, we have to check some conditions that, okay, so if we need to see uh, this is the midpoint, and we have to see the product of this potion value and the spell value. So we can, because you can see the potion and product, this can be big. And if you're noticing, the success is basically a long value. So the product of two integers can be very big, and they might end up becoming a long. So in this case, we have to have a long data type for product, and it have to convert at least one of these numbers, uh, spell time. Uh, we can actually do it once. We can just take the long spell and we can convert an integer to spell. In the case, we don't have to do the conversion here. And potions meat is basically going to be the potion we are just comparing against. So if product is greater or equal to success, in that case, what do? We can basically uh, say that any value in the sorted potion array at the current midpoint or after is uh, probably a valid or a starting point of every product which are going to be bigger than product, uh, bigger than the success value. And product is greater or equal to success. In that case, uh, the left can be brought up. No, this is going to be right side. So the right needs to be at mid, and else, in this case, the success is not the product is not as high as success. In that case, the left has to be shifted to the right of the midpoint. And once we have a value which is where L and R are the same, in that case, this is going to stop. And uh, if we take the difference between the length of the portions array and subtract the L or R, whatever, they're the same in this point. So let's subtract R, L. This is this provides you the number of products which are higher, as high as success. So this is something we have to store. So for that, we have to create a new integer array uh, that we are supposed to return, and uh, pairs I. So this is the ith value uh, of pair of spells. So this is also the ith value in the pairs array. And now if we just place the subtracted value, and in case it cannot find a product which is higher than success, it's going to keep shifting to the right. And at what point, if L and R are and at the very end, if it cannot find that case, uh, it is going to be the last value of the array, and R is going to be one more than that. And this midpoint that we are selecting is going to be the very last value. And that if it still does not provide a valid product, in this case, L is going to be shifted one more. In the case, L is going to be as high as R, and that is where we're going to stop our binary search. And at that point, R is going to be the very one more than the last value of potions array. And that means we are going to have L equals M. In that case, if there is no value, this is just going to return 0, this value. And that is exactly what we need to return as the answer. And if you notice, this example 403, we can explain later. Let's run it first. Yep, let's submit. Yep, this passed beautifully, but let's also go through some of the examples. So 4, 0, so this example 513, you can notice the first one, we already have sorted potions array. So for this one, the 5 value is going to just run a binary search between 5 and between 1, 2, 3, 4, 5. So the first value is 5, and this is already sorted potions. So this is potions, and this is spells 5, 1, 3. So for 5, we're going to run a binary search. So we have 0, 1, 2, 3, 4, and this is the very end. If there is no value, it's going to have 5. So in this case, we will have the midpoint at 2. And if we just multiply 5 and 3, this is 15. In this can we yeah, we know that this is a valid product greater than 7, and success is 7 in this case. So we're going to, so this is our left pointer. Uh, let's switch the colors. This is our left pointer, and this is our right pointer, right? And this is our mid pointer. And left, right, and mid. And we know that midpoint is valid, so in that case, we can keep our midpoint and shift to the left. So now we just moving to the this at the this point. And uh, now, what is the middle point? 1. And for 1, you can calculate the product. So this position value 5 and 10 is still valid. It's greater than 10 is greater than 7. So in that case, you place a right pointer right here, and we can actually erase those. Now we have a smaller binary search space, and between these two values, uh, our uh, our way of calculating this midpoint is going to ensure we are taking this value, not this one, because we are for an odd number of values, you're going to take the floor division in this case. That means we're going to take 0, and as soon as we just multiply 5 and 0, sorry, 5 and 1, the zeroth value is 1. This is less than 7, so we're going to shift left to here. And this is going to stop the binary search because L and R, these are now the same. So you're going to stop. Uh, and at that point, if you subtract 5, which is the total length, minus the this value 1, 5 minus 1, you end up having 4. So that means this is the first point where we do not have a right uh, product. But everything else after that is a valid product. So we're going to subtract the 0, sorry, subtract 1, uh, and this is, sorry, the L and R is the first value, which is still a valid product. And everything else after that is going to be obviously a valid product because it's sorted and is sorted in an incremental order. So this is the result 4. And for the other example, 5 and 1, let's see what it does. Uh, so for the other example, we have 1 as a spell value. Out of 5, 1, 3, we're taking 1 this time. And the potions is 1, 2, 3, 4, 5. And if we have a left pointer here and a right pointer here, nope, sorry, our right pointer is going to be here. Right pointer is here. So in case we absolutely cannot find a value, it will just, the left should actually end up here. Let's see what happens. So these are the indexes 0, 1, 2, 3, 4, 5, right? And in the binary search, we first of all select this value out of 0, yeah, the 0th index, and then this is what you're going to select. And 1 times 3 is still less than success is 7, right? This is still 3, and this is less than 7. So what we do is we shift our focus to the right. Our left pointer is now here. So this is the search space for binary search. And between, sorry, our left is going to be here because this is small. We are going to move to the right. Right, 1. So this is our search space between L to R. And in that case, between 3 to 5, if we just take 3 and 5, our midpoint would be here. Our floor division, 8 and 4, this is our midpoint. And midpoint is 5. And see, 5 times 1 is still 5 and is less than 7. So we are going to shift our left here. And at this point, this binary search is going to stop at this point. And if we subtract 5 minus 5, you end up having 0. And that's why we basically produced a valid answer. And that's the solution. I hope you liked the explanation. Thank you so much.